Good morning, students. Today I would like to discuss with you about momentum. And my first question for you to think about it for a bit is what hurts the most? A ping pong ball or a tennis ball? So, quite obviously, most of you are going to tell me that a tennis ball will hurt the most. But why? Well, simply because usually, since it's more massive, if you put just a tiny bit of speed, it will have some energy associated with it. Whereas, as this is very light, so the mass is very small. However, if you could, for example, put one of those ping pong balls in a cannon and throw it with a lot of speed, then it could hurt as much as a tennis ball, which is really slow. And why does that happen? Well, all of that happens because the concept of momentum. And momentum can be basically described as mass times velocity. And here, momentum is a vector and velocity is also a vector. Since they are both vectors, they are going to be pointing towards the same direction, right? So if this ping pong ball is being thrown from the left to the right, that's their speed. If you scale with the mass, so if the mass is 1, then this vector will have the same length. If this mass is 2, then this vector will be twice as long. You get it? So P, our momentum, will be a vector with the same direction as our velocity, but it scales with the mass. So in this case here, I've tried to make a vector which is roughly twice as long. So that would mean that this mass is 2. That's quite straightforward. So the points first to note here is if V changes, or more specifically, if it's raised, then momentum will also increase. If there is a resulting force in that body, then, well, by Newton's second law, there will be some acceleration. So acceleration means the velocity is changing. So if the velocity is changing, then momentum will also change. If velocity is increasing, momentum is increasing. If velocity is decreasing, momentum is decreasing. So if you're accelerating, your velocity is increasing. Therefore, your momentum will be increasing as well, and vice versa. So up to now, we have discussed some conservation rules, more specifically the conservation of energy. And now, we will discuss the conservation of momentum. And it's implicit here, but this is linear momentum because it's linear speed, so it's linear momentum. So momentum is always constant unless there is some external force being applied to it. So let's say you've got a particle here that I'm representing by a sphere, and I'm calling it number 1. So it's just moving towards another particle, which is not moving. So let's say that this initial velocity here is v, and let me use the same notation that we have used before. So this will be u1. So it's the initial velocity of particle 1. And this is the initial velocity of particle 2, which is 0. Then they will collide. So you can imagine this as a game of pool. So this is sphere 1 and sphere 2. And depending on what kind of collision, we will have different things happening here. So you might have one particle colliding with the other and losing all its velocity, or it will still move, or they may join together and form a new body. So what I'm going to show you here first is what we call elastic collision. So in an elastic collision, energy will not be lost. So all energy will be transferred from one sphere to the other one. So the final velocity of particle 1 will be 0, and the final velocity of particle 2 will not be 0. Now, this will happen if the masses are equal. Because if the masses are equal, all this momentum from particle 1 will be transferred to particle 2. And since the masses are the same, the momentum at the beginning would be mu1. Let's just assume that mass m, right? So that's our momentum. The second case here, our momentum will be mv2. So if we assume that the masses are the same and the change in momentum is 0, so there's no momentum going out of your system, there's no force being applied to your system, the sum of the forces here is 0. So for example, this velocity will be constant forever, and this velocity was constant before. The sum of momentum is 0, so mu1 will be equal to mv2. So those velocities, they will have to have the same direction here, and they are the same. So the values will also be the same. The magnitudes will be the same, and the vectors themselves are the same. And again, this is what we call elastic collision. A few things to notice here is that this particle here, particle 2, at the beginning, it had no momentum because its speed is 0. And particle 1 at the end had no momentum because its speed is 0 at the end. So all momentum was transferred from one particle to the other one. However, what would happen if the masses were not the same? So let's assume that particle 1 now is much more massive than particle 2. And it's moving at an initial velocity u1, which is constant. Mass of particle 1 is m1 and mass of particle 2 is m2. So collision will happen, and after the collision, mass 1 will still have some, let me just align this. So after the collision, mass 1 will still have some velocity, even though it's less than what it was before, and particle 2 now will be moving. Okay? So we may apply our conservation of momentum here. So let's first find the momentum of each of the particles in those two times here. So we could say this is time equals 0, this is time equals t after the collision. So what about this moment here? What happens? Well, momentum of particle 1 is m1, which is the mass of particle 1, u1. Momentum of particle 2 before the collision was 0 because its speed is 0, and well, speed is 0, velocity is 0. What about after the collision? So this is before. What about after? So after the collision, our momentum of particle 1 will be m1, same mass, v1. The velocity has changed. Now what about particle 2? Now it does have some momentum, which will be m2, v2. So in such a case, since the sum of the momentum has to be 0, since there's no external force being applied here, so sum of momentum is 0, therefore P1 at the beginning, before the collision, will have to be P1 plus P2 after the collision. So the momentum before the collision has to be the same after. So let's just put the values in. So M1 U1 will be M1 V1 plus M2 V2. It's easy to notice here that the momentum from particle 1, some of it was transferred to particle 2, but not all of it. That's why there's still some velocity. And it's fairly easy also to deduce that this velocity will have to be less than this velocity. Actually, in fact, right, just look at the mass here, the product of those, the sum of those products, right? So if you had some huge mass times a velocity here, and now you have the same mass times a different velocity plus something else, and you know that both are positives, then this has to be less than the initial velocity. So some kinetic energy from that particle was lost. Well, not quite lost, but it was transferred to another particle. So in a more general collision, elastic, okay, collision, in which there's no loss of energy, what would happen? Well, let's assume then that this is mass m1, speed u1, and a second mass which is moving, m2 and u2. Now, obviously, u1 will have to be larger, otherwise they wouldn't bounce, right? They wouldn't hit each other because this one would never get to the second one. Now, after the collision, then you will have a lower velocity here and a larger here, right? So if we apply our conservation of momentum, what is the momentum before? So here, m1u1 plus m2u2. After, m1v1 plus m2v2, and that is the relation that you get. Obviously, you may rearrange those things like m1 u1 minus v1. I'm getting this to the other side, all right, and just collecting some of those terms, and I may get m2 to the other side, so I'll get v2 minus u2. You know, you can do all sorts of things, like for example, you can find the ratio between the masses if you know the speeds, right? For example, the ratio between the masses here would be v2 minus u2 over u1 minus v1, which mathematically is the same thing as u2 minus v2 over v1 minus u1. I've just swapped both here, so I've multiplied by -1 on top and -1 down below. But you don't need to do that. I mean, they will give you basically the same idea. Now, just as a side note, I have written the proof for elastic collision, but I will upload as a separate video because you don't really need to know that, but just for fun, if you want to check how it works. Now, the other kind of collision that we have is inelastic collision. So in an inelastic collision, what happens is that after, so I'm going to draw blocks here just because it's more reasonable. Look, two things, they will collide, and after the collision, they will be stuck together. So both will be moving together as if they were one mass, and that's it. So let's just work our conservation of momentum here. So if this block is mass m1, this is m2, speed here, u1, right, velocity I mean, velocity here is 0, it's not moving this other one, and then both will be moving with the same speed, and the mass here will be then m1 plus m2. So conservation of momentum, what is our momentum before the collision? So before the collision, the only block which was moving was m1 with the speed of u1. So that's our momentum. After the collision, the mass of our object is m1 plus m2, and it's moving with the a velocity of v. So if we want to calculate v and we know the initial velocity and the masses, we may rearrange that, and what we'll get, we can divide the left hand side by m1 plus m2. So we'll have u1, right? So those vectors, they should be in the same direction, which multiplies m1 over m1 plus m2. So that would be the formula for inelastic collisions. And what is really important for you guys to do is to check your physics data booklet, because most of those equations, they are given, so you don't have to memorize them. Now, there are a few things that we can observe here if we take a look at this ratio. And let's ask ourselves a few questions. For example, what happens if m2 is much smaller than m1? Well, that would mean that m1 plus m2 is about the same size as m1, right? If m2 is so small, think of this as, I don't know, 100 kilograms and 1 gram. So it's so freakingly huge that this is not even to be considered if we sum those two, right? So m1 plus m2 would be about m1. And if we make this ratio here, it would be 1, right? If m1 plus m2 is about m1, so m1 over m1 plus m2 will be about m1 over m1, which is around 1. So that would mean that our final velocity will be our initial velocity. And that makes total sense. Why? Well, because if the second mass is really tiny, like a freckle, I don't know, some dust particle here, it will not stop our block at all. If it's really massive and moving with a huge speed, and this is just stopped and not moving at all with a very low mass, then it won't really affect this first mass when it's moving. So they will join together and this mass will not really change much. Another point that we may observe is that this value is always less or equal than 1. Right? If we assume that those two are the same, it would be equal to 1. In principle, in reality, it will never be equal to 1. It would be always less than 1 in reality, in practical terms. So what does that mean? Well, that means that this speed will always be less, well, this one will always be larger than the final one, right? And that makes sense because since you have more mass, now it's harder for you to move. So this is always less than u1, than the initial velocity, and that's expected. Now let me show you an interesting case. What if I have two blocks here and I hold them in such a way that there is a compressed spring in the middle of them? Or you could visualize this as two magnets and I'm holding them together or really close to each other in such a way that they feel the magnetic force from one another. And what's going to happen here is there will be a force trying to make them move. So if I let them go, in any of those cases, they physically, they can be described in the same manner as forces, right? So when we let this spring go, those blocks, they will move in opposite directions, right? So let's draw this in a better way. So there you go. Here we have our situation before I let the spring go and after the spring goes. So if we sum our momentum here, it would be 0 because there is no speed. And in this case here, the sum of the momentum will still have to be 0. Because if you think about the forces which have been in action here, they are inside of our system. So the force that was exerted to make this block A move to the left is the same that made block B move to the right. So what does that mean? Well, what is the momentum of block A here at the end? Well, if its mass is mass A, it would be MA VA. That's the momentum of block A. What would be momentum of block B? Well, same thing, but MB VB. So if those two summed have to be 0, that will mean that one speed will be negative. Take a look at this. For this to be 0, that has to mean that one of those two will be in the opposite direction for the sum to be 0. So what happens here is that, well, if our frame of reference is x positive to the right, that will mean that our acceleration here will be negative. And that's what we can deduce from the conservation of momentum here. So V1 and V2 will have opposite directions. If the masses are the same, they will also have equal magnitudes. But if the masses are different, then no. The velocity will be inversely proportional to their masses. So that also means that more mass will make its speed be slower. And yeah, that's an inversely proportional relation. So let's take a look at one example now in which we have trucks colliding. So let's assume this situation here in which there is one truck going to the right at full speed, U1, and there is a second truck here which is just in the traffic lights minding his own business, and this one doesn't really see the other truck and just collides with it, and there's some final velocity. Now I'm going to give you some information about those two trucks. So this truck was very loaded, so its mass is much larger than the other one. So this is 4.5 tons, so 4,500 kilograms. And I'll tell you that this initial speed here is 1.8 meters per second. The mass of the second truck, which was very light, look, there's nothing here on top or inside, so it was unloaded. So M2 is really small, 1,500 kilograms, so 1.5 tons, and speed is 0. All right, so what is the final velocity? That's it. So you could, I'm giving you the drawing here so you can see that this is an inelastic collision. So again, inelastic collision, they will stick together, and now they're moving as one block of mass, in this case 6,000. So let's model this problem. Now that I've drawn this in a beautiful way, let's just model it in a more physical way. So here we go. Now I've just drawn some blocks. So block M1 moving to the right, speed U1, which is 1.8 meters per second, and U1 is 0, mass 4,500. The two, after the collision, the two will join, the mass will be the combined mass, and there will be some new velocity. So to solve this, we can use conservation of momentum. So the momentum before the collision will have to be equal to the momentum after. So change of momentum is 0. What is the momentum before the collision? Well, M1 U1. That's the only mass which is moving. The other mass is still, it's not moving. Second situation here, after the collision, my mass now is M and my velocity is V. So to find V, which is our final velocity of the two combined trucks, it would be M1 U1 divided by M1 plus M2. I basically divide there and just used M1 plus M2. So what would that be? Well, m1 is 405,000, u1 is 1.8 meters per second, and m1 plus m2 is 6,000 kilograms. Now, I've omitted all units here simply because this is in kilograms, meters per second, so our result will be in meters per second. Now, 4,500 and 6,000, that's 3/4. So if we multiply 1.8 by 3/4, we will get 1.35, or you could say approximately 1.4 meters per second. So if we are asked what is the final velocity, you should not only say that it's 1.4 meters per second, but to the right. Since this is a vector, you will have to specify what is the direction, not only the magnitude. Now, I think those examples are enough for today. In the next few lessons, we will be dealing with impulse and some applications involving both momentum and forces. And those are a few of the last topics that we will discuss during the chapter of mechanics, at least in the standard level. All right, I wish you all a very nice weekend and see you all next time.